Okay, good morning, and good to see you again, man. Like I said, this class is focused on precalculus, and the things that we'll be talking about during the series would be the key components of precalculus, many of which have been done in Algebra 2 already, right? In particular, we'll focus on trigonometry and the different aspects of trigonometry, but especially focused on what I will call analytic trig. It includes trig identities, trig equations, and so on and so forth, right? So that's going to be important. We are also going to look at things like law of sines and law of cosines. Have you done this already?
Yeah.
Law of sines, yeah. You do them again in college. The interesting thing is that they just repeat themselves over and over and over again. So we're going to do that. Then what we're going to add that you may not have done is we're going to add vectors. Okay. So that's one of the focuses of the things that we'll do in this unit. Then we will move on to what could be a new topic for some, matrices. This one you use to solve equations, you use to do simultaneous or linear equations that look really complicated. You can put them in a matrix and you can solve them. That's the other thing that we're going to do. Is not particularly complicated, even though it can get really complicated, but it's a very elegant way of solving problems. So then we'll do that, and then I think another thing that we should look at that's useful later on in college is sequences and series. Have you done that?
Yeah.
Okay. So again, this is the kind of thing you do in algebra, you do in precalculus, then you do in college. Why do they repeat it so many times? I'm not sure. Like where I went to school, we didn't have to do many topics in different places. But anyway, so we get that. And then this is what I find many students struggle with. And that's because it's not like algebra at all. It's a different way of thinking, right? So probability is another thing that we're going to look at for sure, because I think once you know your probability, and actually statistics, a little bit of statistics. And then I also want to look at logarithms and exponentials. Again, these are things you cover in algebra. However, in precalculus, they take it a few steps further, right? I want to devote most of today's session to trig identities. Okay. And that's why I have this sheet here that basically summarizes most of the trig functions and trig laws. I would also provide a sheet that has some problems that we're going to start looking at right now on these trig identities. Okay. There's a sheet that I have that talks about proving trig identities from easy to hard. Okay. So we're going to do a few of those ones and see how they come out using just this sheet here. And then towards the end, we're also going to do a quick review of some vectors as well. I know vectors may be a new topic, right? So tell me a little bit about what you've covered. Do you have your textbook here for math? I don't think so.
Oh, no.
No. What are the things that you've covered this semester under trig?
I think we've done most of the chapter. It's like, we've done graphs, we've done unit circle.
Okay.
Yeah, and then now we're on identities.
Trig identities. Okay. And what do you think about trig identities? Have you been able to do a lot of practice on them, or you are still at a place where you're trying to get more practice? What would you say?
Probably more practice.
Okay. Alright. So let's try a few ones. Doesn't matter if you know how to do them or not. Let's just try them now and see where you might be on them. So I'm going to give you a couple of them. Let's start with the sheet that I call the easy sheet, and then we'll proceed to. Hey, how are you doing?
Pre-cal.
Yes. You're welcome. My name is Mahama. I was just taking him through the topics that we're going to be looking at in this series. How do you say your name again?
Aaron.
Aaron. Okay. And what school do you go to?
Monovist.
Awesome. Are you already in the precalculus class or you're in algebra too?
Trig.
Okay, cool. So that's what I said. This is going to build on what you've done in algebra to trig. And what I was just saying was that we're going to focus on some particular topics. This could change based on what I see the needs of the class are. At the same time, I want it to be focused on problem solving ability. Because you see that you do this in algebra 2 trig, you do it in pre-calculus, you do it in college as well. So what is it that is going to make it better for you in terms of how well you do is how many problems you can solve. So instead of going through all the concepts each time, what I'm going to do differently is I'm going to say, okay, this is the topic, you may have done some of it, you may not have done some of it, right? How about we try to solve problems that would help you see if you remember? If not, we would deal with the concept at the time that the question comes up, alright? So he has just, he's doing trig right now. What topic are you doing in school right now?
Law of science.
Law of science, okay, so that's fine. That's still part of the series. So the difference with algebra 2 trig is that some of the questions may be a little bit more difficult in pre-calculus. But what I want you to take away from these series is how would you solve a problem that looks really difficult? And how can you do it efficiently? So it's going to be beyond doing the topics themselves, right? You've seen most of these before. You've probably done logs before, haven't you? Yeah? You've done probability before, haven't you? Sequence and series. So the chapter names are the same, but the content gets harder and harder as you go through. When you go to freshman year of college, you see all these things again. And you're like, didn't I just do them? And then they start from easy, then it goes harder, right? So we're going to go through all of these. What I've given you, if you can look at this sheet, is something that talks about trig identities, proving them from easy to what? Hard. Okay? I'm going to just pick a few of them and ask you to, in the next 5 minutes, do them for me to see where you are, okay, on that. Later on, I would also give you a worksheet on logs and exponentials to see where you are on that, okay? Now, I'm just trying to see how we gauge the depth of coverage we give to these topics. There are a few others that are not here, but as time goes on, we'll put them along. So the question that I want you to look at, and if you're going to take the class by video, I'll give a link to this. I want you to look at doing question number 1, 2, 3, and 5. Actually, so they are the in-class assignment. That's something we're going to be doing a lot. We're going to be doing in-class assignments, and then we are going to talk about how you do them. It's okay if you can't do them right now, okay? Evan, have you done identities already? Yeah, good. So, you're going to try questions 1, 2, 3, 5, actually, and 10, I would say. 1, 2, 3, 5, and 10. And take a few minutes to try that, and let's see where your memory is. I gave you the handout so that if you forget what an identity is, you can look at it and check it out.
Number 1 means before that. This one this is number 1, right? Then next time I have to use this 3 to solve this result. Private is 2.
So again, I don't want you to worry about whether you can do it or not. I want you to try it. And let's see where you're going. No pressure, okay? I'm just checking. So even as we are practicing these, I'm going to send around to Erin another sheet of problems, but this one has solutions at the back. I'm going to write the questions on the board. Question 1 says cos theta plus, keep doing what you're doing, and just writing this on the board. Prove. Okay, I hope this shows in the video. Have you finished number 1? How about number 2? Where are you now? Okay. You doing the 4th one, you mean? Yeah. Okay. Where are you?
I did the wrong sheet.
Oh, you're doing the one with the solutions?
Yeah.
Don't worry about it. That's still good practice, okay? Alright, so let's just do it all together. So the idea would be, like I said, lots of practice problems that we'll do from week to week, right? So this one, for example, I don't want you to just know how to solve it. I want you to know that what is the fastest way to do it, right? So let's take question 1 on here. I'm going to clean these and then let's look at question 1. Even as Erin finishes up. What does it look like? So let's say you didn't know how to do this problem and then you just saw it. What I would recommend you do is you say, well, first of all, you don't do anything to the right hand side, you let it be. And you know secant is what? Theta is the same as 1 over cosine what? Theta. So you know that. Alright. What is here that it does not belong? Cosine belongs, this thing belongs, this one does not, right? So you need to change this to sine over cosine. That's what you did. So what did you do here? You had cosine theta plus sine theta times sine theta over cosine theta, right? And remember, we are proving from left to right. Yeah. So that's fair. So when you do this, what did you end up doing? You find the lowest common multiple. Did you do that? Okay. So this one is cosine of theta. I mean, I have to divide this by 1 just to show that I'm trying to find the lowest common multiple. So what do you get here? Cosine squared theta plus, what do you get here? Sine squared theta, right? That's what you got. If you look at the identities that we have on this, that's called the Pythagorean identity. It's cosine squared theta plus sine squared theta is equal to 1. Pythagorean identity. So we got that. So the top is 1 over cosine of theta, which is the classic definition of what? Secant of theta. But it's not the answer that I'm interested in. I'm interested in identities. If you start the wrong way, you can get stuck, right? So you just, first of all, don't rush to solve any identities problem. Inspect first. So first rule, inspect. This belongs, it kind of looks like this. This belongs as a variation of this. This does not belong. So this is what you want to work on, right? So every time you see an identity problem, and about after we finish these 5, we'll go on to the so-called medium and hard ones. Some of them are going to look really messy, but you need to identify what do I change first. Alright, so the second one, how, I know what you were doing a different set, but what did you do for the second one? The one that I'm about to write down on the board, it just says cotangent theta plus tangent theta is, so it says prove that cotangent, this is question 2, cotangent theta plus tangent of theta is secant of theta cosecant of theta. So we're not touching the right hand side. In college, you're probably going to see that there are going to be problems where it's very difficult to do the right hand side, the left hand side, and you start from the right hand side. But as a general rule, don't touch the right hand side, leave it. So what is missing here? What do you do differently here? This is something in terms of cosine, this is something in terms of what? Sine. So what did you do on this side?
I changed cotangent to, I changed the entire left side to cosine theta over sine theta plus sine theta over cosine theta.
Okay, so cosine theta over sine theta plus sine theta over cosine theta. Now at this point it becomes more of a, what would I say, algebra problem. So I have a student from Pali who's really smart and does really well, but he struggles a lot with these identities, and I figured out his problem was not the identity, it was the algebra that he was missing out. Because here, if you don't use the proper algebra, you wouldn't get the answer, right? You need to find the lowest common multiple, which I'm sure you did. Sine theta cos theta, right? So what do you do? This becomes what? This becomes cosine of theta squared. Because sine theta, so this is cosine of theta squared, right? Plus, what does this become? Sine of theta squared or sine squared theta. Similar thing, Pythagorean identity is just 1 over sine theta cos theta, which is back to that. So not a big deal, that's why they call them easy problems. Alright, question 3 I'm not going to do, but the idea is the same. Let me write question 3 down for those who are going to watch on the video, so that you see what the question is. But I'm not going to do it, I'm just going to say how you do it. Were you able to do that?
Yeah.
Okay. So question 3 just said sine theta plus sine theta cotangent squared theta is equal to cosecant theta. So Wesley, I know you're trying to do it. Let's just focus on this. So let's look at what we are trying to prove, right? This is 1 over sine theta. Okay. This already looks like it's in the right form. This looks like it's in the right form, but this one is different, right? So this is the one you change. We're not going to do it, but this is the one that you have to change. So what I'm trying to encourage you is that in identity problems, look at what is out of place. So this is out of place, so I want to change it to cosine squared theta over what? Sine squared theta. And when you simplify with a lot of algebra, you get here. So that's doable. It just looks weird at the beginning. Now, the other one was question 5, right? I'm going to do question 5 because it requires some kind of expansion. Do you remember how to expand this? Okay. So from the list that we have here, these are the sum and difference identities if you have this one. So the idea would be, what's that? Do you know how to expand this? You just check what are those ones called again? These are the sum / difference identities. You see that? Mm. So the thing that you want to realize is that if you have cosine of, here we use alpha and what? Beta, but it's just A and B, right? You see there's a minus at the bottom, but then it's on top here. So if it's minus, it becomes plus. So to do it, it's just going to be cosine of pi, cosine of theta, right? Plus sine of pi, sine of theta. So this is basically what I'm trying to show you here.
Yeah, that's okay.
Yeah. Then at this point, it's not algebra anymore, but it's your knowledge of the unit circle. Correct? So the unit circle says that cosine of pi, what is it? What's cosine of pi? So it's important to know what cosine of pi is. It's important to know what sine of pi is, because the final answer had something in terms of cosine. So what is it? From the unit circle, what's cosine of pi? Exactly. I don't know how you learn the unit circle, but the easiest ones to know are obviously the ones at these corners, right? So the unit circle just means that from here to here has a value of 1, and so on. So if you look at the x-axis, there's no y value on this side, it's just what, an x value. Y is 0. That's why cosine of 0 is 1 and sine of 0 is 0. That's what it is. And if you're on this line, also on the unit circle, there's no y value here, right? But the x value here is negative 1. So it's just going to be negative 1 and what? 0. So even without knowing your unit circle, the ones on the axis you should know. Because for example here, y is 1 but x is 0. Here y is negative 1 and x is what? 0, right? So at least the ones on the corners I want you to remember. So here, x is 0, y is 1, x is 0, y is negative 1. This is 3 pi over 2. This is pi over 2. This is 0 or 2 pi, and this is just pi. So that's it. So I always tell my students, memorize the unit circle knowing just these things, and the rest of it you can fill in. So what do we get as cosine of pi is negative 1. So this is negative cosine of theta. Sine of pi is 0. Plus 0. So you've proved it. That one was easy. Again, like I said, this is a precalculus class, but you know how to do this even from algebra 2. So precalculus is not magic. Precalculus is, let's remind you of everything you did in algebra 2 trick, and then let's step it up a little bit further. So at the beginning you're going to think, oh, but I've done all of this before. Then over time you're going to think, no, this doesn't look the same anymore, right? Because when we start talking about a plane is flying at a certain altitude with a certain bearing, and the wind is blowing at a certain, speed, what is the final ground speed of the plane? That's the trick. But you need to know some vectors. Those are applications. So in precalculus, we're going to focus a lot more on applications, but they still want you to remember all the basics that you've done. Any questions up to this point? Did you kind of follow that? Okay. I also realized that at the beginning, unless you do tens of them, you're not going to know how to expand them by hand. Yeah. Alright. I'm not going to do the number 10, but I'm going to write it on the board anyway. And I want us to talk about how would you do it. So again, the focus is on how would you do it. I'm not so worried about if you get the final answer right. I'm just concerned about how you would do it. So let's say the question says, prove that tan theta plus cotangent theta divided by tan theta cotangent theta is equal to tan theta plus cotangent theta. So this one is, did you guys get to it? Take 2 seconds to think about it and tell me what is the most efficient way to do this. Yeah.
Split up the left side into tangent theta over tangent theta cotangent theta and plus cotangent theta over tangent theta.
Ah, okay. That actually makes a lot of sense too. Yeah. So you're saying, I like to use box. You're saying if you have triangle plus box, this is algebra, right? Divided by triangle times box. This is the same as triangle over triangle times box, right? Plus box over triangle times box. This is basically what you're saying. Take each of them and divide by that. So this would cancel this, right? And this will cancel this. So you basically end up getting 1 over, sorry I'm using box and triangle, it's just something that I picked up when I was in school. It's okay. I see it this way easier. So you get 1 over this, 1 over that. But how do you end up getting that?
1 over cotangent is tangent.
And then 1 over tangent is what? Cotangent. Okay? How would you have done it, Leslie?
I just look at the bottom and then I change tangent to like sine over cosine and then cotangent equals cosine over sine and it just cancels.
It became 1. So that's another way to do it. So this is another way to do it. They both work. All of you had it right. Okay. Another way to do it is, because I have tangent and cotangent here, no sine and cosine, my first advice is do not change it to sine and cosine, because the answer is in tangent and cotangent. And also, even though you divided it by these two, normally that works, and it works in this case as well. That's not the most efficient. Look, cotangent is just 1 over tangent. So in this place, what I would have done is I would have said, okay, I'll keep tangent the way it is. What's that with me? Look, I'll keep tangent the way it is, and I'll define cotangent as 1 over what? Tan theta. So this thing becomes 1. And then you get that, right? So in one step you get it. So my other advice with doing identities is spend more time thinking before you do it. Because if you spend 10 more seconds thinking about the efficient way to do it, then you can do it faster. But if you do the first idea that comes to your head, you may get it right, but you may spend too much time doing it, right? So first thing, look to see what is out of place. Second thing, look to see if there's more than one way of doing it and pick the fastest way of doing it, correct? So that's basically what this one was. You tell me, in school, what are the kinds of identities problems that you've had that you find particularly difficult? These are supposed to be normal. Have you run across things that are particularly challenging for you with identities? Yeah. It's one of the things that you can easily get tricked. There are a few topics in precalculus that you can get tricked. It doesn't matter how good you are in probability, somebody can trick you. It doesn't matter how good you are with identities, somebody can trick you. Because you don't see what they're asking you immediately, right? Wesley, any questions on this? I wanted us to do some of the slightly harder ones. The one that they say medium hard, right? So those ones, you have them on the sheet I gave you. But let's take 2 minutes each to do question number 1. I think let's do it one at a time. At this time I don't want to give you a long time. I'm going to write question number 1 on here. So if you're watching it on the video, this is the question that we are doing right now. It says, prove that So instead of just doing it, and I want us to think about it together, right? So there's something happening here. When I was a student, when I see this, I would be a little bit scared. What on earth am I supposed to do with these 4s? And how did they become 2s in the first place? That's the thing that would scare me. But if you look at the fact that there's a minus here, and you look at the fact that there's an identity that's it's an algebraic principle that says a squared minus b squared is the same as a plus, this is algebra by the way, a plus b, a minus what? B. So if you don't remember this may be very difficult for you to do. Because this is really the trick to it. So now you say, but I have 4 here and I have 2. Okay. So I say fine, this is fine. So this is a4 minus b4 is the same as a2 plus b2, a2 minus what? b2. Can you see that? So once you get this one, which is derived from this algebraic, then you can do this one. Right? So we are saying here a is what? Sine, right? And b is cosine. So this becomes sine squared theta plus, oh, then you begin to get excited because there's something with this. And then this is sine squared theta minus cosine squared theta. That's what this expression is. But you have to remember that to get that. What is sine squared theta plus cosine squared theta? It's 1, right? So this whole thing is 1, and what are you left with? Sine squared theta minus cosine squared theta. So that is what makes, this is a medium problem, but what makes it hard is if you forget this algebraic principle. If you forget this, then I don't know, I actually didn't know any other way to do it. Okay? If you don't know how to expand this, it becomes really challenging. So another general point about any problem that you don't know how to do, skip it and go to the next one if you have many questions to do. Don't be a hero and try to do the problem one after the other. So this is just a test principle that I always use. Do the easy ones and come to the hard ones. The other thing that I would say about these types of things is, if there's one thing you remember, do that one thing first. I could have said, let sine squared theta be equal to a and cosine squared theta be equal to b. And this becomes a squared minus b squared. I could have said that. I didn't do that in this case. I'm going to say, so the other way to do it that may work for you, this is how I've done it. This is equivalent to 1. So you get sine squared theta minus cosine squared theta, which is similar to what you want to find. But as I said, the other way to do it is to say let a be equal to sine squared theta, b is equal to cosine squared theta, right? So this one is a squared and this one is what? B squared, and then I can use this to do it. That's the other way to do it. Again, if you haven't seen it before, you haven't used it before, that could be a challenge, but everything has to do with practice, right? Okay, let's do a different type of identity proof. So on the sheet that I've given you, I want you to try question number 4. Question number 4, just say sine theta plus cos theta all squared. I'm going to write it on the board for those watching the video to see what we're doing. Question number 4 under medium hard. Question number 4. So let's just get back to this and see how you do this. Okay. Since you don't want to work from right to left, you want to work from left to right, it still helps to think about what are they thinking about when they say sine 2 theta. Because there's an expansion for sine 2 theta. So what I'll say is, the hint here is, even though I don't want you to work from right to left, the hint here is sine 2 theta is the same as what? I mean, you would practice, I'm sure you know it anyway. It's the same as sine theta plus theta, right? And if you look at the expansion for that, this is simply sine theta cos theta plus cos theta sine theta. I mean, I'm doing it step by step. This is simply 2 sine theta cos theta, right? This is what the hint is. Because you're going to get something in here that may look like that. So this one squared is just sine squared theta plus 2 sine theta cos theta plus cosine squared theta, right? That's what that expansion is. We know this is something we recognize. This is the magic thing we recognize. Yay. Magic. This is one. Whoever developed the models for this is really smart. Every time I see sine squared and cosine squared and there's a plus in between, I'm happy. I know I can get rid of this big stuff. So this is simply 1 plus 2 sine theta cos what? Theta. Right? And that one is the same as what? Sine 2 theta. So there's no other way around it. You have to do a lot of these things to get them right. So this is just 1 plus sine 2 theta. Again, what you learn from here is step by step. So if my goal is to get to this door, right? And this is not just about math, but I have a chair in front of me. I'm not going to worry about the door yet, even that's where I'm going. I'm going to worry about the next thing in front of me. So I'm using this as an illustration. Don't worry about proving this. Do the first thing, which is, in this case, expand that. When you expand it, it's like you've taken the chair out of the way, and now you can go to the next step. So, this is not a difficult problem necessarily. For some people, it could be. You have to take a big pie and break it into small pieces. We have a very popular African proverb that you don't eat an elephant at once, right? You eat it in small bits. And at the end of the day, you end up eating the whole elephant. But if you try to swallow the entire elephant in one thing, I don't know how big you are, but it doesn't look possible, right? So I always say, what is the first thing that you can do? Do that. And then after you do that, it may open the door to the second thing you can do, and the third thing you can do. So that's the step-by-step way of doing it. Don't try to say, oh, but what is that? And many teachers will give you partial credit if you get here, but you don't know that this is the same as sine 2 theta. So at least go to the point that you can. We're going to do a couple more identities problems. And today I want you to learn something that's semi-new, maybe vectors. I want us to talk a little bit about, have you done vectors before? It's also in physics and it's in math. There's a thing I don't understand about the US system is, why do you do it in 2 different places? Anyway, so we're going to do a few more identities problems, and then I want you to learn something new. I want you to learn something different, so we'll do vectors. Anyway, so let's take a couple more identities problems here. I would like you to try question 11, which I'm going to write on the board. Question 11. Question 16 as well. Question 11, question 16. So why don't you do question 10? Question 9 as well. So the questions that you're doing are question 9, 11, 16, 17. 9, 11, 16, 17. So 9, 11, 16, 17. I'm going to write those questions on the board on the left hand side for the video students to see. 9, 11, 16, and 17. Okay. So I've written those ones on the board. Take a few minutes to do them. Again, I'm not interested in the final answer per se. I'm interested in what is the process that you're going through when you think about it. Again, I'm not going to give you so much time to do all of them. I just want you to think through them, okay? And we'll take a 5-minute break and then we'll come back and we'll do the vectors. You have the questions anyway, so you can always do them on your own. let's talk through them. Let's just talk through them. So, based on what I've been saying so far, you see that I'm very interested in process, your thought process. I'm not mistakes. You can make a mistake no matter how hard you try. Sometimes it's not because you're not smart. It's just that mistakes happen to everybody. What is an efficient way to? First of all, I'm trying to get one here, right? What's an efficient way to do this thing? What would you do? Would you, first of all, the question is, would you change this to sine and cosine, or would you work with what you have? That's it. Correct. That's the correct answer. Work with what you have, and then what would you do?
Probably, well, I found like the common denominator, and then I just set the top equal to the bottom, and just cancel them both out to equal to 1.
Yeah. So it can't, when you did that, you got it as well, right? Yeah. So after you do so many of them, you're going to recognize a pattern. A pattern that in this type of problem, don't change it to sine and cosine. There's no sine and cosine on this side. Find the lowest common denominator. Boom. We got it, right? So in this type of problem, what would you do? If you don't know the Pythagorean identity for this, then you're in trouble, because I don't want you changing this to sine and cosine at any point. What's the way to do this?
1 plus tangent squared theta is equal to secant squared theta.
Alright, so it's called secant squared theta over cosecant squared theta. One of them is 1 over cos and one of them is 1 over sine. It flips over itself, so you get sine squared theta over cosine squared theta, right? And you do that. That's what you get. So the thing is just, what is the key to solving this problem is knowing what this stands for. This is the same as secant squared theta. Once you get that, this problem becomes doable, right? I would just say depending on the student, some students will say change it to secant theta over cosecant theta, all squared if you want. It doesn't make any difference, but if you want to do that, and then you realize this is the same as 1 over cosine, so it goes to the bottom, 1 over sine, it goes to the top, and then you get tangent, and you square it. If it works for you that way, that's fair. Okay. Don't you just like it when they mix sine and cotangent and all of that stuff? So, what is going on in question 16 here? What do you think is going on? I don't know if you can do question 16 without expanding it. How would you do it? There's more than one way of doing it, by the way.
Change the top to 2 sine theta, cosine theta.
So you change the top to 2 sine theta, cosine theta, and you want to change the bottom as well, right? So the secret is to remember for question 16. For question 16, keys, right? Sine 2 theta is equal to 2 sine theta. And by the way, it's important to just memorize these. You don't have to start this from scratch, right? And then cosine 2 theta is just cosine squared theta minus what? Sine squared theta. Boom. This is what you need to be able to do this problem. The rest of it is algebra, really. So if you put 2 sine theta cos, so that's what I was thinking. If I say 1 minus cos 2 theta, I could think about it this way. If I were doing it in my head, I'd say 1 is the same as cosine squared theta plus sine squared theta, right? And I'm subtracting this from it. So I'm getting rid of one of these, and then I'm adding that. So what you're going to get is you're going to get cos. So let's just do the denominator. We haven't had a problem that's hard yet, but sometimes I advise students to do the numerator separately and do the denominator separately. So in this case, the numerator is straightforward. So I'm just going to do denominator, right? And I'll combine it later. What I'm saying is if I have 1 minus cosine 2 theta, I could think about it as 1 is cosine squared theta plus sine squared theta, right? That's one way I could think about it. That stands for 1. And then minus, we already know what this is. Cosine squared theta minus, so cosine squared theta minus sine squared theta. So what do you get? Cosine squared theta gets rid of cosine squared theta, right? And then this becomes sine squared theta minus sine squared theta. So it's what? 2 sine squared theta. That's what you get there. So you get 2 sine squared theta in the denominator, and then you have 2 sine theta cos theta in the what? Numerator. Is that what you did? Yeah. Because this one can be a little bit of an albatross if you don't think about it like this. So you can get, then what do you get here? This is the same as 2 sine squared theta. So I would, in a more, these are not the most complex ones. In a more complex problem, I'll do the numerator by itself. But then some students do that, they forget to combine them at the end because they get so involved with one aspect and they're like, oh, is that what I'm doing? No, that's not what you're doing. You have to remember that if you break it up, you need to bring them together, right? And you don't have to write the denominator, no. You can just say, this is what I'm doing, and then you go through it. So again, now the two questions are the same. You have to look at the question by inspection and then do it. Okay? Alright. How would you do number 17? Actually, number 17, I've never done it before. What would you do? What is the key to question 17? So let's talk about this. I want you to think about keys to problems. What would you do that will help you do question 17 well? You're trying to get negative tan squared theta, right? On the right hand side. And I'm even asking myself, how did they get negative to come out of that? That's what you guys are doing. I want you to identify the key before you solve the problem. Don't solve it before you know what you're asking for, right? Yeah, so you need to remember cos 2 theta. You probably want to break it down into cos squared theta minus sine squared theta, right? Where are you? Okay. So this is that what you go here? 2. Okay. Then the top becomes the. What do you do with the top? So you're right. The denominator is correct. Okay. So you see that you got the denominator to be some number. That works because you should get sine squared theta over cosine squared theta somehow, right? But there is a factorization that I want you to factorize the top. Factorize the top. That's the way to solve the numerator, right? Yeah. Alright, so let's do 17 together. The keys to the problem are this. Recognize that tan squared theta is the same as sine squared theta over cosine squared theta, okay? So I want you to recognize that somehow you need to end up with recognize sine squared theta over cosine squared theta is equal to tan squared theta. The reason I want you to think about it this way is that when you know what this one is supposed to look like, you can find that. Okay? That's key number one. The other thing is factorize the numerator, right? Factorize. I wish there could be the same set of keys for everything, but almost every problem has. When we do a lot of them, you can put them into categories, right? Like all of these can be put into 5 or 6 categories in general, and then you know that this category is how you do it. So here you have to factorize it because if you did that, you get 2 outside the numerator. I'm factorizing the numerator. 2 cosine squared theta minus 2 is 2 outside cosine squared theta minus what? 1. Doesn't this look so similar to saying sine squared theta plus cosine squared theta is equal to 1? Right? So look, if I flip this that way, I get sine squared theta is 1 minus what? Cosine squared theta. But this is cosine squared theta minus 1. Hence the negative sign. That's the only way they could have had it. So this, if you bring this down, this is the same as what? Negative 2 sine squared what? Theta. Right? Because 1 minus cosine squared theta is sine squared theta. But here we have cosine squared theta minus 1. That's why this becomes negative 2. Because this is not exactly that. Okay? I mean, you could do that, you could bring things over, whatever. So that's your numerator, you get that. And then for this one, so the other key, of course, is to expand. Why did they do that? Somebody wanted to factorize, somebody wanted to expand. So expand cosine of what? 2 theta, which is cosine squared theta minus sine squared theta, right? Added to 1, I always like to break the 1 into, if possible, cosine squared theta plus what? Sine squared theta. So the denominator then becomes what? 2 cosine squared theta, right? So in the end, if this is the numerator. This is the numerator. If the numerator is negative 2 sine squared theta, what do we get? We got negative 2 sine squared theta over 2 cosine squared theta, which is negative what? Tan squared theta. That's that. The reason I decided to start with trig identities is for many years of teaching this is the one part that shouldn't be too hard, but students find it hard. That's because of all these types of weird stuff. Expand, factorize, remember all kinds of things. How do you get out of this type of challenge? Do a lot of them. And also, no matter how many you do, there's always going to be a problem you can't do. I've seen that. I've done this for many years. Sometimes I can see when I'm like, right away, I don't even know how to start, right? They can make it really complicated. So don't be a hero and try to do every identity problem you see. If it doesn't look like you can do it in 1 minute, do something else and come back to it. But in general, the keys are identify what is different, think about the final answer as you do it, and don't break things down if you don't have to break it down. So that's that. We'll take like a 3-minute break, restroom break, and when we come back, we're going to learn something new. We're going to learn vectors. Now, vectors is really practical. It's not theory, it's practical. But we'll start with a theoretical basis and then we'll build that. We won't finish vectors today, but when we get to the point where we do applications, it's going to be so interesting. You're going to see if you're flying a kite in the air, why is the kite going somewhere that you don't want it to go? If an airline pilot wants to go from here to Las Vegas, why don't they just travel in the direction they want to go? Why do they have to arc the plane a certain way so that they get where they want to go? All of that is vectors. It's not very difficult. It's still a trig, a different variation of trig, right? So that's what we'll do. We'll revise things that you know already each week, and then we'll add things that you may not have done yet. And for the things you know, we may make it a little bit more interesting as well. Okay? Yeah, so let's take this break and then we'll continue with vectors. We haven't finished trig yet, by the way. I'm not saying we finished trig. I just wanted to do one portion of trig. Went to the restroom.
That's what I see you do for, right? If I equals 0, I less than n. Keep looking until there's no
It's off that logic, and what is the thing there? 1, 1, 0, 1, 1, 1.
yeah. If 1, 1, 2, 1. I will use that like
Okay. Alright. So what is a vector? Vector mathematics is one of the most practical things that you can do. Imagine that you are swimming from maybe San Jose to San Francisco and the current is blowing in the other direction. I'm going to show you in a minute. So what you are trying to do is not necessarily what you're going to end up doing. Why is that? And math has come up with a process of trying to figure out how to get to where you're going, taking into consideration what is blowing for you or against you. Right? And the way we do this is something called vector mathematics or vector physics, depending on what you're doing. There's not much of a difference between vectors in math and vectors in physics. Okay? I mean, the applications are different, obviously, but the math is similar. So I'm going to take a practical example. You swim, right? So let's say that you swim in this way. So what, you have a body mass or you have a weight, and you're swimming in this direction. Right. Let's say that there's a current that is facing you, and the current is coming this way. Where do you think your final destination is going to be? Down, right? So this is where this is going. This is where you're going. So in the end, even though this is what you're trying to do, this is where you're going to end up. You see what I guess did? This is the current blowing in this direction, the water current, or maybe somebody doing kite surfing. This is where you're trying to go. This is where you end up going. So see, we can represent this by a letter. Let's say that's you, W, that's your vector. Let's say this is the current C. This thing is called your resultant. Your resultant is where you end up based on what else is happening to you. If the current were not blowing, you would go exactly where you want to go. Right? This could happen also with an airline pilot. If they want to fly a certain way, really they want to be going straight, but this is the air current, they end up going down. So if you are a smart person and the thing is blowing this way and you want to still go this way, what would you do? Exactly. So maybe it's more difficult as a human being to do that, but as an airline pilot, you could actually angle it up. So instead of doing this is where you want to go, right? So you probably want to angle your thing like this, and then when it blows you, you end up going like that. But you need to know what the math is, what the angle that you want to incline yourself is, so that you don't end up going too low or too high, right? Because if you're trying to go this way, you don't want to angle yourself in such a way that you end up going up. You still wouldn't go as high as you're angling, but this direction is important as well. Okay? So the speed with which you're trying to travel is important, the direction is important. There are two things that are important to know in vectors. There's something called a scalar quantity, and then there's something called a vector quantity. So a scalar quantity is something that has magnitude. So the mass of this chair, I don't know what the mass is, to be fair. Let's say it's 10 kilograms. I'm pretty strong, 2 fingers of 10 kilograms. That ain't bad. That is a scalar quantity, okay? So examples of scalar quantities are, they will only have magnitude. They have no direction. They get magnitude. So an example is mass, is a scalar quantity. Then we have something called a vector quantity, or just a vector. In addition to having a magnitude, this is what? Direction. So vectors have both magnitude and direction. So a scalar quantity is something that, I guess that's a number, that's it. Nothing else. Okay? But a vector quantity has both magnitude and direction. I'll give you an example of a vector quantity. An example is weight. See what we just did there. Mass is a scalar quantity, but weight is a vector quantity. Weight has a direction. So if you look at weight, actually weight is simply the same as mass times acceleration due to gravity, right? And this acceleration to gravity is working only downwards. That's why weight is a vector quantity, but mass is not, right? So when we represent something as a vector, we usually will show what direction is it going. Is it going up, down, left, right, whatever it might be, okay? So that's the thing that we're going to realize. The vector has both magnitude and direction. That's the key thing to know about vectors. Vectors have many operations that will surprise you. They are all very, well, I'll say easy. But let's see, how do you represent the vector in a plane? Let's just check that out. When you've drawn lines in the past, you've had a point A, you've had a point B, and then you've drawn a line. Does this line have a magnitude? Yes, it has a distance. Distance is a magnitude. But you usually don't put any direction on it, do you? It's just a line. I mean, it can go this way, it can go that way, it can go wherever it wants. However, if I put something like that, this is a vector. So it has a distance and it has a direction. I'm telling you, you're going that way. Not any other way. So that's a vector. Usually vectors, but not all the time, are represented as what we call position vectors starting from the origin. So if I have a point B, usually they use P, but let's use B for a reason. Starting from the origin, you go this way. That's a vector. And you can use a letter U or V or whatever. So OB is a vector, and it can be written many ways. It's written with a hat like that. So I'm telling you, you're moving from the origin to what? B. Alright? So let's say I like to walk around about. So before going to, I go here, and then I end up going where? here, right? Let's call this A. Maybe my cousin Andy lives here and my sister Beatrice lives there. So before I go to Beatrice's home, I go to Andy and then I go here, right? So what is happening here? I start by going here and then I end up going here. The place I want to get to at the end is called my resultant. It's from the word result. Resultant is where I end up wanting to go. So I can write the formula with all these three. Check this out. The formula is going to be, for me to get to OB, I go to OA and then I go OB, AB, right? So look, OB, which is my resultant, is simply OA plus what? AB. That's where I end up. So this one I call my resultant, usually with double arrows. That's where I want to go. There are many reasons why this could happen. So I can write the formula for this. So AB, vector AB, this is a general formula, is simply what? OB minus OA. See that? AB is simply OB minus what? OA. And every time you see a vector written like this, it's going to be the second one minus the first one. So this is our first general rule, either in math or in physics. That if you see a vector like that, a vector can also be written, by the way, like this. This is actually, in US textbooks, this is the vector notation. They will do that and they will do that. Okay? Something like that. Any questions on this? So magnitude, direction, you want to memorize something like this. AB is simply OB minus OA. Of course, similarly, any letter, right? PQ is OQ minus OP, and so on and so forth. We're going to do some operations pretty soon about how all these things work and how you can solve your problem of you're trying to swim somewhere and some other thing is pushing you somewhere, and where do you end up? And what angle do you choose to get to where you want to get to? So direction is measured using angles, right? And distance, of course, is the magnitude of the vector you're dealing with. Okay, so let's see some of the properties of vectors. We're going to, let's see what examples they have. So we have vector addition, vector subtraction, vector multiplication, all of that stuff. You know how we say that if you have 2 plus 3 is the same as 3 plus 2. What's this property in math? What is it called? Yeah, this is commutative, right? So vector addition is also commutative. So if I have a vector u plus w is the same as w plus what? U. Vector addition is associative as well, right? That's the one where you have the brackets and stuff. So vector addition is associative. We have a plus b plus c is the same as a plus b plus c. So vector addition is what? Associative. It is commutative, is associative. We're going to see that in a minute. How about vector multiplication? In this series, we are not going to look at multiplying a vector by a vector yet, but we're going to look at multiplying a vector by a scalar. So, let's say I have a vector u. This is a vector, okay? This is a scalar. A scalar is just the one that has no direction. If I multiply k by u, is the same as multiplying u by k. I mean, again, common sense. Almost all the algebra principles work in what? Vectors. Okay. Now, what if I gave you v plus negative v? What do you think this is going to be? What would that be? This is a vector, you add it to a negative vector. What will happen? Like, that's correct. So it's like saying, I run this way, and I run back. I'm back to where I started, right? That's what happens. So I don't want you to think about vectors as anything different. I want to encourage you to just see it as something doable. It's not harder than any of the other things you've done, but it's more practical. Okay? Alright, so there are a few other things that we need to know about vectors, which is what is the magnitude of a vector. Let's say I give you a vector AB. So obviously this will have a component X component and a what? Y component. How do you find the magnitude of a vector? So let's say the point B has an X and Y component. And I'm going to call this vector small b. So small b, the magnitude of small b is the common distance formula, which is root of x squared plus what? Y squared. You've seen that before. Yeah? So if you want to find the distance from A to B, just root of x squared plus y squared. Same thing. There's something called a unit vector, however. We're going to define what a unit vector is. Just like you have things in the unit circle, you have a unit vector. We are just going through definitions right now, nothing serious. A unit vector is a vector divided by its magnitude. So unit vector is a vector divided by its what? Magnitude. That's what a unit vector is. Okay. There's something called the head minus tail principle, which is what this is. I haven't used it. I guess call it the HMT principle. It doesn't mean, you don't have to know what this is. It just tells you, you take the head of the vector, subtract the tail of the vector, that's how you get it. That's what this one says actually. This is the head, this is the what? Tail. That's how you get the value of the vector. So, assuming that I gave you a vector, I gave you 2 points. I'm going to make this different. I gave you a point here. Let's say this is x is 6, y is 3. Okay? Let's say this is x is 2, y is 1. And I call this p, and I call this what? Q. Okay? How would you find the vector PQ? So the vector PQ, which can be written like this, I could also just call this the letter U. Any letter, really. What is it going to be? First of all, the notation is going to be this. This is vector notation. One way of doing it. Remember this formula? Head minus what? Tail. So it's going to be the x value minus the x value. This is 6 minus 2. The y value minus the y value, which is what? 3 minus 1. Which ends up being the vector PQ is equal to 4, what? 2. So that, it's almost laughable because it's so straightforward. I have 2 points. This is my direction, obviously. I cannot do this minus that. It has to be this minus this, right? Head minus tail. So the vector PQ given 2 points is just this point minus this point, and then this point minus what? That point. And as you can see, I'm not starting from the origin in this case. It works whichever way you do it. So that's one thing to know. Alright. This is of course when you're using the XY coordinate system. I can represent vectors in a different way, which I'm about to show you. The fun is not in the definitions. We just have to agree on the common language so we can communicate. That's what we're doing these things. It's a common language so we can communicate. Vectors can also be written in terms of what we call I and J. Don't get confused with complex numbers. You've done complex numbers. Don't get confused with that. I used to get confused with complex numbers a lot, but it's not. So, we have the I and j coordinate systems instead of the x and y. So j would represent your y-axis in this case, I will represent your x-axis. So I can also write a vector as, and this I is not the I in complex numbers. I can write a vector as AI plus BJ. So I take the x value and I just add I to it, and I take the y value and just add B to it. It's just a model. Somebody came up with this, they could have used x and z, but they used I and what? J. If you wanted to, instead of writing it in this form, 4 and 2, this vector could have been written as 4i plus 2j. This is one way of writing it. This is another way of writing it. So if you see that, you see this is the x value and this is the what? Y value. Those are some. The reason they do these things is that it's so much easier if you wanted to do addition to be thinking about it like this than to be thinking about all these brackets, right? So we're going to do a few easy. This is going to be so easy, you're going to laugh. Easy operations on vectors, okay? One of them would be, let me see what exercises they have here. I'm going to give you a few vectors and you're going to tell me what the answers will be when you add and subtract. Alright, questions are coming on the board. It says, if vector v is 2i plus 3j, w is 3i minus 4j. It says find a 2v plus w, b v minus w. Just try it in class and see what you get. So again, this is the vector 2, 3. This is the vector 3, negative 4. It says find 2v plus w. Remember, it works exactly like math. Nothing special about that. And then I'm going to add C, find magnitude W, well, V and W. So 2V plus W, V minus W, find magnitude V and W. So you find the magnitude of that. Remember, x squared plus y squared root is the magnitude. Same here. I know you can do it. It's part of the vector, so do it for extra practice. So no credit here. Just extra practice. Okay, so this one is simply just 2 times 2, right? Let's find 2v. 2v is simply what? 2 into 2i plus 3j, which gives you 4i plus 6j. You add that to w. W was what? 3i minus 4j. Add that, you get 7i plus 2j, right? That's the first one. So let's not even bother doing this one. This is just arithmetic. Now, I'm going to do just one of the magnitudes and I'm going to do the one with the positive. So magnitude of v is simply root of 2 squared plus what? 3 squared. Which is 4 plus 9, which is what? Root of 13. That's how you find the magnitude. So let's throw a little bit of a wrench into this. How would you find the unit vector for V? What is the unit vector for V? So the definition for unit vector again, unit vector is this, the vector over its magnitude, right? So that's pretty straightforward. This is going to be 1 over root 30 times 2I plus what? 3j. So I'm not going to rationalize. We can rationalize it and all that stuff, but I'm not. 2 over root 13I plus 3 over root 13 what? J. That is the unit vector for V. So unit vector is 2 over root 13I plus 3 over root 13j. So why is this called unit vector again? Try and find the magnitude of the unit vector and see what you get. So this is 2 over root 13I. This is the final answer. But if you find the magnitude of this, what would you get? It's called a unit vector, right? So what is the magnitude of this vector, the unit vector? What is the magnitude? Has to be 1, right? Because of the word unit. So the magnitude of this vector is going to be this squared, right? Plus this squared and the root. If you do that, you get 1. That's one way you check to see if your answer is correct or wrong. Every time you do the unit vector, the magnitude has to be 1. Because if I square this, I'm going to get 4 over 13. If I square this, I'm going to get 9 over 13. If I add them, I'm going to get 1. So unit vector magnitude is always equal to 1. Okay? So that is what that would be. Now, another thing they can ask you is find the direction of the vector, right? These are both vectors in their own right. So I want you to tell me, based on what you know from trig, how would you find the direction of V and how would you find the direction of W? The angle it makes. So really what this one is, if you want to draw it on the axis, I'm not going to do it for you, but I'm going to draw it so you see. Let's draw the vector V. It's 2I plus 3j. If I put it on the x and y axis, I'm going to assume that it's a position vector starting from 0. Goes to the point, x is 2, y is 3. Let's call that this point, right? So this is the point 2, 3. That's what it will look like. So the direction will be, what angle does it make? This is here, it could have been anywhere. So how will you find this angle if you know x is 2, y is 3? What is the best way to do it? So basically this is 2 and this is what? 3. What identity would you use? Tan, cosine, sine, which one? Tangent, right? Yep. So you need to know this angle. So this is going to be tan inverse of the y value over the what? X value. So the direction of a vector is tan inverse of the y value over the x value of y over what? X, or b over a, whichever way you write it. That's how you find the direction of a vector. Therefore, I want you guys to find me the direction of this, direction of that. Find the direction of V and find the direction of W. If you don't have a calculator, that's okay. Just write the formula down. And pay attention to quadrant, right? Because this and this are in the first quadrant. This one not necessarily. Yep. So this is just going to be tan inverse of this However, I still suggest that you put it in the right. This is in the first quadrant, so it's going to be less than 90, right? This one is in this fourth quadrant, so it's going to be above 270 degrees. That's important. That direction is going to be like this. What makes vectors even more interesting is that usually when it comes to flying objects, kites and planes, they give you bearing and not angle. What's a bearing? So a bearing is an angle measured from the north. So if I tell you the bearing of a plane is 60 degrees, it means it's 60 degrees from the y-axis and therefore 30 from the x. In trig, you learn to do everything measured from the x-axis. Sometimes in vectors, they'll give you a bearing measured from the y-axis. So you need to write that down, and then you would find the x-axis, okay? Well, we're going to do a lot of practice over time. And I actually think vectors will help you with your trig, because it helps you to see how trig is applied, actually. Like in this case, you realize, oh, this is tan inverse of this over that. You did it in trig, okay? So that's why this is practical. Let's do some more examples in the rest of the class. I think I have some cool examples here. Oh, one more definition even before we do examples. You can also write that in terms of cosine and sine. Okay. You can represent a vector in terms of cosine and sine. I think that's probably what makes it okay. Let me, I'm going to draw something here. This is the angle theta. Again, we said this was J and this was what? I. If I know that the magnitude of this line OA is V, what is the x component? The x component is going to be what? V magnitude cosine of what? Theta, right? What is the y component? V magnitude sine of what? Theta. So instead of writing it as I and J, I could do, if I'm doing it like this, this is magnitude V cosine of theta, comma magnitude V sine of theta. Are you with me? Or I could write it like this. It would be magnitude V cosine of theta I, that's in that form, plus magnitude V sine of theta J. So this is another way you can represent a vector. You're going to see that as well. Yeah. In my mind, it's not such a big deal. If you know your trig, then you can apply it like that. Okay. All right. Let me pull up some examples that might help. I don't want us to get too deep today into the really technical stuff, but I want us to at least understand what the basics are. Okay. Let's see. This the book just says access your understanding. I'm just going to have us. I'm going to read the question and then you're going to tell me what the answer is. It just says A and then it puts dash. A dash is a quantity that has both magnitude and direction. What is that? So a vector is a quantity that has both magnitude and direction. Okay? It says if V is a vector, I gave you this answer already. If V is a vector, then V plus negative V is equal to, we know that, it's okay. So this is another one, just checking our understanding of the thing. If the magnitude of a vector is equal to 1, that vector is called a unit vector. Okay. True or false? I haven't told you this yet, but just guess. True or false? Mass is an example of a vector. False, yes, because mass is a scalar quantity, right? Force is an example of a vector. True or false? Yes, force has a direction, so it is true, right? Okay, so let's do what I call some scale building. This is what you're going to need to do all those fancy flight and swimming problems. I'm going to draw some things on the board and you're going to try and figure out how do you find the resultant. So, what do I mean by how do you find out the resultant? You can just tell me what you think. I have a vector going this way, I have a vector going this way. For simplicity, let's use u and v. Where would the resultant be? The end result of it. How would it look like? So actually the resultant is that. Okay? And what is cool is that this actually is a parallelogram. You can take this is v again, and this is u again. So usually they'll give you a vector like this, u and v, and they ask you to add them. The idea is this is the resultant of the vector going that way. That's just one thing to keep in mind. This was u plus v. So I'm going to make it more interesting. What would u minus v look like? I want you to sketch it on your sheet. What would u minus v look like? So this is u and this is v. But I said keep u the way it is, right? Add it to minus v. Minus v means v is going in the opposite direction. And see if you can draw the resultant. You just draw it on your sheet and then we'll use together on the board. U minus v. Okay, so I mean the cool thing is you just have to reverse the direction of this, right? Instead of it going that way, it's now going this way. Boom. Do you see that? So if this is going this way, this is going this way, this is minus v, and the resultant is something like that. Okay. Okay, this is cool. What about? Oh, this is going to be scary. Minus u minus v. So minus v, we have it already, right? Minus u comes down this way, so it's going to be that. Okay, cool. How about v minus u? How do you do v minus u? Try it first and let's see. V minus u. So minus u comes down this way, and therefore this is somewhere like that. Okay. That is super cool. Do you want to do like a real life problem? Okay. This we'll see. This is a bit tricky, but we'll see. It says, write this down. Two forces. Yeah, write this down. I didn't print this for you guys. Two forces of magnitude 30 newtons and 70 newtons act on an object at angles of 45 degrees and 120 degrees with the positive x-axis. As shown in the figure, they will give you the figure. I'll give you the figure in a minute. So I'll read it one last time. Two forces of magnitude 30 newtons and 70 newtons act on an object at angles of 45 and 120 degrees with the positive x-axis as shown in the figure, which I'll give you in a minute. Find the direction and magnitude of the resultant force. Find the direction and magnitude of the resultant force. That is F1 plus F2. So this is the diagram I'm about to draw on here. It's part of the question. Sometimes they don't give you a diagram and you have to figure it out. This time they gave you the diagram. Pardon the fact that my drawing is not the best in the world. So you got this. They call it magnitude F2 is 70 newtons. And then the angle it makes is 120 degrees. And they have magnitude F1, 30 newtons, and then it makes an angle of 45 degrees. So that's the diagram that they give you. And of course this is y and this is what? X. So it's almost like the forces are lifting something up, right? One of them is lifting it this way, the other one is lifting it that way. That's what it looks like. Because that's the direction the force is going. So let's talk about this before you do. So there are many ways of doing this problem. Okay? One way is what we started by doing. You imagine where the resultant force is going to be. It's going to be somewhere in the middle, right? But also think about this. This is a more powerful force than this. So the resultant is going to be tilted towards that force. Not here. Towards that force, right? And also this is a much wider angle. That's another reason why it's tilted. If you use trig, your life will be easier to do this problem. Okay? Why do I say that? Remember the last thing I wrote was you can have the magnitude V cosine of theta I, right? Plus magnitude V sine of theta I. But every force has an x component and a y component. So in physics we call it resolution of vectors. So you're going to take this force of 70 newtons and break it down into its x component and its what? Y component. You're going to take the force of 30 newtons, break it down into what? X and y. The resultant force is the sum of the two forces. You add the x components together, you add the y components together. You're going to get a number that has an x component in terms of cosine and a y component in terms of what? Cosine, right? That's how you would find it. And then, when you get that, you can find the angle that the resultant force is acting. So why don't you do that? Even if you don't have a calculator, break it down. So take the F2, break it down into x and y components, right? Take the F1, break it down into x and y components. And then when you do that, add the 2, that's the resultant what? Vector. And when you get the resultant vector, based on the numbers you get, you can find the direction of that resultant vector. Right? So try that. Resolve F2 into its components, resolve F1 into its components. And that's how you do it in real life, by the way. This is not theory, this is how you would actually do it if you were doing a problem like that. There's another way of doing it, but this is, I find this the easiest way to do it. Yeah, give it 3 more minutes, and then I'll break it down into how they want you to. This is an application of almost everything we've been doing. Yes, I've jumped 3 steps ahead for you to see what it looks like, but we'll fill in the gaps, okay? So yeah, take a couple of minutes and see how you do it, and then we'll talk about this. Again, this is useful for physics, it's useful for math. Alright, so let's just do it. This is the last thing we'll do. So, I like to think in terms of steps. So the first thing is resolve the vectors into their vertical and horizontal components. So resolve, don't do this in the test, this is just for class. Resolve the forces into vertical and horizontal components, right? Each of them, not just one. So let's do that. F2, well, the vector F2, not the magnitude, this is a vector, is the magnitude of the vector F2 cosine of the angle, right? I plus the magnitude of the vector F2 sine of the angle J. We know the angles, so we're just going to use them, exactly. So this is simply 70 cosine of 120i, right? You just use the angles with respect to the x-axis, plus 70 sine of 120j. That's what it is. That's your vector F2. Let's distinguish between the magnitude and the vector. The vector is not the same as its magnitude. But that's the vector, and that's the direction, now we get that. And then we take F1. It's simply going to be, it's going to be 30 cosine of 45i plus 30 sine of 45j. That's what that one would be. So that's how we resolve the vectors, right, into their components. In this case, I didn't even need to use a diagram. The diagram is always recommended because sometimes the forces go in the opposite direction, so you need to be careful. Then my step 2, add the vectors. Yeah, just add the vectors. So what would it be? It would be, oh, you guys who know the unit circle. What's cosine of 120? So this is 90 plus 30, so that's 60. So that's half, right? But negative half because you're in the second quadrant. So this is going to be negative 35i, right? So F2, well, okay, let me write that here so that this is just negative 35i plus, this is a positive one, right? This is 35 root 2j, I think, because sine 120 is root 3 over 2, positive, 35 root 3 over 35 root 3 over 2j. Is that it? Yeah. Then we go to this one. 45 doesn't matter. It's root 2 on 2. So this is just going to be 15 root 2i plus 15 root 2j.
35.
This, oh, there's no 2 here. Yeah. That's correct, you're right. So this is 35 root 3. Thank you for noticing that. 35 root 3j, 35i. And this is that. So now that you have that, you add the vectors. Of course, you have to add I to I and J to J, apples to apples and oranges to oranges. So, I mean, resultant vector, I'm just going to call it the resultant force, R is equal to negative 35I plus 35 root 3J. Don't be surprised if you see something exactly the same in physics, because that's how you do it in physics as well. And it's the same type of problem. That's 15 root 2J. That's how you get it. I'm not going to add them. That's what you do if you did that. And if you're going to use a calculator, you need to break root 3 down to its form and stuff. So you're going to get just two numbers, right? One in terms of I and one in terms of what? J. That's your resultant force. You can find the magnitude of it and the direction. The direction is tan inverse of the J value divided by the what? I value. So that's how you find the resultant force in this case. Okay. I've jumped a few steps so that we can see a practical example of it. Next time we would do a little bit more of a different aspect of trig and then vectors. I don't want to spend the entire session teaching you something new. I want to deepen your understanding of something you know already and then something that you probably haven't done yet. I think that's a good balance, right? Because you're going to do precalculus maybe the next semester or when are you guys doing it? When are you doing yours? Next year, yeah. So the idea would be something that would help you with what you're doing now, which trig does, maybe a little bit harder problems over time. And then something that, but these are all part of precalculus. I mean, we're not doing algebra 2 trig, we're doing precalculus. And then something that you can use. I'm going to give you an assignment on how to find the speed of and direction of an aircraft. Okay? Do you have your phone so you can take a picture of it? And also, obviously, anything that we didn't do here is also an assignment. So this one. See if you can use what we've done so far. It's a little bit challenging, but see if you can use what we've done so far in vectors to do that. And also, the ones, I'll try and see if next time I can print copies for you. The ones that we didn't do for the identities, I think you should try and do them on your own. Okay? Like this one has solutions and answers at the back, no solutions. Just do them. Just find the exact values of sin 45 and cos 15, all of that.
Just this page.
Yeah, this page, and then we didn't finish the other page. Remember that we're doing this other one, that the one we started with, the medium, easy, and hard thing. Anything that we didn't do, I want you to do it. They're mostly doable. If you get stuck, think about the algebra. Right? It's usually not the trig that's the problem, it's the algebra. So your assignments will be the vector problem, obviously, the rest of these easy and hard problems, and then this other sheet. Because most of the work has to be done on your own. Okay? There are three things that I learned, actually this last week. I'm reading this book called, it's a very interesting book, if you have time. I know you guys don't have time. It's called Quirky, and it talks about the most innovative people in the world. Like, it talks about 8 people: Elon Musk, Marie Curie, Isaac Einstein, really sharp innovators, right? And they talk about the concept called self-efficacy that I really like. Like, how do you get to a point where you really believe in your ability to get things done? There are 3 things. And this is relevant for math and poetry. The first thing is personal experience. Basically, for you to develop self-confidence, you need to do things on your own and fail until you can do it. That is the strongest way that you can learn anything or be confident in yourself. Self-efficacy. The second way is what they call vicarious experiences or vicarious experiences. So vicarious experiences is basically observing someone else do something. like I do something on the board, you look at it, you may or you may not understand. But that's another way to get confident, because someone else can do it, therefore I can. Then the third way is just through external motivation, is what I would call it, the way they describe it. Or basically lecturing. You just hear someone say something and you learn from it. Okay. It's not necessarily teaching, but you learn from listening or someone encouraging you to do stuff. But above all, this is the number one. And this ties into what they say all the time, practice. So if you haven't done something before, most of the time you don't know it. Even if it looks like it makes sense, unless you start to do it, then you can tell, oh, I can do it. So I would encourage you, even in sports or math, try it. Last week, somebody came to teach a guitar class at my regular job. I have an engineering job. And he's a very good music player. He brought about 8 guitars to the class. And I was so scared of trying, because it's like, man, I'm going to look like a fool in front of everybody. It's so messed up. And then he came to me and said, look, it's okay. Try it. There's no way you can learn by just listening to me, showing you this is the G chord and this is the whatever chords he was talking about. Try it. And then when I put my finger on it, I was like, oh, it's not as scary as it looked at the beginning. But I didn't want to look like a fool because, Anyway, so anything that you're doing, try it. It's okay to fail at doing something. That's normal. That's just life, right? Cool. So we'll end here today. But I know I have given you a lot of homework. Just practice it. And also you can bring in current things you're doing in school that you want to be talked about. Because we have 2 hours, it's a lot. I want to deepen your current knowledge, and I also want to add new things to it. Cool? Alright guys. Have a good rest of your weekend. So where is Monte Cristo located?
On
Semester?
yeah, thanks.